Hi, everyone. My name is Aimen, and this summer I conducted investigations into the sensitivity of the novel COVID-19 biosensor as created by the Daniels Dimensional Materials Lab last year. So as we all know, the COVID-19 pandemic has really changed our world with 91 million confirmed cases and over 1 million people dead from the virus in the US alone. So this necessitates an urgent need for rapid, ultra-sensitive diagnostic tests. The first test I'll talk about here is the RT-PCR test, which uses DNA amplification, and it is the gold standard for diagnosis, being extremely sensitive, having a limit of detection of only 100 copies per ml. However, it is very time-consuming and requires trained personnel. The other type of tests are rapid tests. They utilize something called antigen antibody binding. They only take about 15 minutes, but they only detect infections with high viral loads and also have a high instance of false negatives. So the Daniels lab sought to combine the best of both current diagnostic tests. So they created the quasi-freestanding epitaxial graphene biosensor. It is able to detect the COVID-19 virus using an antigen antibody binding reaction in typically less than a second. So it's faster than a rapid test, and it's more sensitive than a PCR test with a limit of detection of only 60 copies per ml as opposed to 100 copies per ml. This biosensor uses something called ELISA-based sensing, which is where the COVID-19 antibody is immobilized onto its surface and then reacts with a sample solution. However, the caveat with this biosensor is that the substrate upon which it is constructed, silicon carbide, is very expensive. So what is the sensor exactly made of? It's made of quasi-freestanding epitaxial graphene on silicon carbide substrate, which is immobilized, the graphene has a pi network, which consists of many delocalized electrons, which allow for the biosensor to have a large response to physical stimuli. There's also a lot of strain induced on the graphene from the silicon carbide substrate. And how exactly does this biosensor work? After certain organic structures like the crosslinker or the antibody, et cetera, bind to the structure, electrons move to the quasi-freestanding epitaxial graphene. This serves to remove tensile strain from the cation pi interactions present on the surface due to the crosslinker binding. The strain then moves through the graphene, distorting the lattice and altering the cation pi bonds. This then results in certain changes in resistance of the graphene that we can actually track. So an alternative to the biosensor that the Daniels lab made is making a biosensor out of a material known as hexagonal boron nitride on graphene. It is a commercially available material, unlike epitaxial graphene. It is also a monolayer as opposed to being a bilayer. And much like epitaxial graphene, it also has a high carrier concentration and is able to separate the graphene from its substrate. It essentially is a sheet of graphene with hexagonal boron nitride in plane. So next, I'd like to compare certain electrical properties of h-BN-Graphene with quasi-freestanding epitaxial graphene in order to illustrate why it was thought of as a potential alternative. So both have a similar sheet mobility as well as similar carrier concentration. However, quasi-freestanding epitaxial graphene has a much higher resistance value. So the question that I investigated this summer was a hexagonal boron, a hexagonal boron on graphene-based biosensor on silicon dioxide substrate should not have the desired sensitivity, as the quasi-freestanding epitaxial graphene biosensor sensitivity is due to certain strain interactions between its silicon carbide substrate and the epitaxial graphene. So in this experiment, first, I actually made hexagonal boron nitride on graphene sensors and then compared them to epitaxial graphene biosensors. I first etched, cleaned, and added metal contacts to each of my samples, then conducted Raman spectroscopy to establish a baseline phonon structure, and then did atomic force microscopy or AFM to visualize the material's uniformity and topology. Then I coated each sample with a crosslinker, which serves to covalently bond with the epitaxial graphene and non-covalently bonds with the antibody. This allows us to actually clean off the antibody using a sodium chloride solution very easily. Next, I conducted Raman spectroscopy again to track the shifting of the G peak, which is actually related to the graphene's carrier concentration and strain. The graphene's G peak is essentially the in-plane vibrational mode or the stretching mode of the graphene. Then I coated each sample with an antibody coating using the ELISA method, and then tested each sample by applying a constant current and then measuring the voltage change of the sample to see the response of the sensor to the COVID-19 antigen. Here are my results with regards to Raman spectroscopy of the hexagonal boron nitride on graphene biosensors. Here you're looking at the shifting of the G peak of the graphene in these biosensors. We found that there was only a partial left shifting of this G peak, as opposed to a complete left shifting that's seen in the quasi-freestanding epitaxial graphene biosensors with each additional layer added to the biosensor. So when I was actually testing the hexagonal boron nitride biosensor, there was no marked change in voltage when I dropped the 1 attogram per ml of the COVID-19 spike protein onto the sample surface. However, when I was testing the quasi-freestanding epitaxial graphene biosensor, there was a marked change in voltage when I dropped the 1 attogram per ml of the COVID-19 spike protein onto its surface, about a 20% increase in voltage. So major takeaways. We found that there was only a partial left shifting of the G peak in the hexagonal boron nitride on graphene biosensors, as opposed to a complete left shifting that's seen in the quasi-freestanding epitaxial graphene biosensors. This points to a limited functionality of the graphene that's due to the fact that hexagonal boron nitride on graphene simply does not experience the same strain effects that are seen in quasi-freestanding epitaxial graphene with its silicon carbide substrate. Therefore, the hexagonal boron nitride on graphene biosensors are simply not able to sense the 1 attogram per ml of the COVID-19 spike protein. Therefore, we have proved that the quasi-freestanding epitaxial graphene biosensor is indeed superior. So moving forwards, now we know that the sensitivity of the epitaxial graphene biosensor is due to its interactions with its silicon carbide substrate. We'd like to be able to use the epitaxial graphene biosensor to detect other viruses like monkeypox and Lyme disease. And we'd like to make this biosensor into something like a breathalyzer test that can be placed in public areas like hospitals, cafeterias, etc., in order to test for presence of any virus. Great. Thank you all for listening.